Thanks for having me. Yeah, I'm David Krueger. Here's my talk title page. I'll just go ahead and get right into it. Oh, first I'll tell you a tiny bit about myself. So I've been concerned about the social impact of artificial intelligence and X-risk in particular since around 2009. Um, and when I first heard about this, it was from blogs written by people who were not studying artificial intelligence, at least not in an academic context. So, less wrong and the like. And I really didn't know what to make of this. I mean, it sounded like a very plausible argument that we should be worried about this at some point in the future. But I thought that we were probably at least 100 years off from sort of real AI, because all of the AI systems that people were building at the time looked like they just were never going to scale to intelligence, or at least it was a very brute force approach that would take just way more compute to have any shot at it. And that all changed when I heard about deep learning in 2012 from Jeff Hinton's Coursera course, which I was lucky enough to binge watch at just the right time. And in that course, he talked about two developments in deep learning, recent developments that really blew me away. And the first was ImageNet, which I think everybody would be familiar with. The other one was actually a text generation demo that Ilya Sutskever did in 2011 using an RNN to generate text, natural language, one letter at a time. And this really, even more than the ImageNet result, blew me away because it showed, one, that AI systems could be creative in some sense, and two, that they were capable of learning things like how to compose words and how to make novel words, using this really simple approach. So I was lucky enough to get into deep learning, and I did my master's and my PhD at Mila starting in 2013. And then I just started about a year ago as a professor at Cambridge, finally, having finished my graduate studies. So I'm building a research group there now, focused still on deep learning to some extent, mostly trying to understand deep learning and sort of understand the capabilities and limitations of deep learning systems, so that we can understand the alignment challenges that we face better, and then of course alignment and existential safety. One thing I want to plug here is that I am hiring postdocs. I've extended the deadline a little bit, so everyone watching this will still have a chance to apply if you're interested. And I'm sort of always looking for more people to join the group as well, but right now really want to find a couple good postdocs. So if you or anyone is interested, please let me know and check out the ads. Anyways, so to get into the content of the talk. So the first thing I want to talk about is just what is AI alignment and how does it relate to existential safety. So I think there are actually three separate things that people mean by AI alignment sometimes. And the first two here are really technical problems of how do we get AI systems to do what we want, or what's sometimes called intent alignment, how do we get them to try to do what we want? And the try maybe goes in quotation marks because we haven't been able to rigorously formalize that. You might think that it's a little more clear what the intention or motivation or what the AI is trying to do in a reinforcement learning context, where you can just say that it's trying to optimize the reward, but even that doesn't necessarily hold up. And in general, when you have something like a foundation model, it's really unclear how to figure out what the intentions of the system are, or to what extent it's appropriate to even talk about it having intentions. But the other way that people are using this term is really just to rebrand this same community that's existed for 15, 20 years of people who are worried about AI destroying the world. And so basically the AI existential safety community. And this is a community of people who are not purely technical AI researchers, and who are certainly not purely doing machine learning research, who are trying to figure out what are the most effective interventions to reduce the chance that AI is going to destroy the world and kill everybody. And this is a socio-technical problem because there are aspects of it that, like the governance of AI systems, that might have technical aspects, but also are much more about things like how do we, use this technology, and how do we coordinate society, both sort of from a principled point of view, but also just practically right now, what are the steps that we can take to maybe make people more aware of this problem, or make them take more effective action to address this problem. So that could mean things like trying to slow down AI research or redirect it towards things that are more relevant to safety. And so actually, I think this is a really important point, because I think people in this community often think too much about this as a technical problem and view solving this technical problem as roughly equivalent to reducing AI X risk to an acceptable level. And I think that that's really not, well, I'll just say it's not the picture that I have of the way this works. So in my mind, we are always going to have this safety performance trade-off, or you could also think of this as like an alignment capabilities trade-off. And people also sometimes call this like the alignment tax. But basically, I think there are all these things that you can do to increase the safety of your system, like doing more testing, trying to keep a human in the loop, making sure that you actually understand how the system is working, and saying, if it's not interpretable, if we're not confident that we understand how the system makes its decisions, we're just not going to use it. And each of these things is going to take a significant and likely an increasing hit on the performance of the system. And so if we want to stay in a regime where we're able to do extensive testing, we're going to have to develop and deploy systems slower. If we want to keep a human in the loop, we're going to have to limit the rate at which the AI system can make decisions, and so on and so forth. Maybe one more I'll mention is this long-term planning thing. So instrumental goals really fall out of the long-term thinking and long-term planning of systems. And so we might remove what I think is one of the biggest concerns about AI by just keeping them myopic. But of course, that's going to really limit them. And I don't think that these trade-offs are going to go away. I know that's probably a somewhat popular opinion, but I think still the way that people are approaching this problem, in my mind, only makes sense a lot of the time if you think that we really can, get rid of this trade-off, or at least make it very marginal. So in some of like Paul Christiano's writings, for instance, you'll see him talk about the idea that we can have something like a 10% alignment tax, or less than a 10% alignment tax. And to me, that is just wildly optimistic. I don't see that happening. Now, one thing that people say in response to this kind of picture, this strategic picture that I'm painting of the problem that we face, is aren't safety and alignment actually just kind of part of capabilities? Because everyone wants systems that are aligned, that are sort of acting in accordance with their intentions, and that are safe, are not going to like do something unexpected and hurt them or hurt other people. And I think, there's some truth to that, but I think it sort of misses a couple important points and sort of misses the big picture. So for one thing, there's a big difference between safety and existential safety. So like safety in some senses, this AI isn't going to kill me or people that I care about. It's very unlikely to do that. Let's say it has like a 1 in a million chance of killing me or anyone that I know and care about. But if that 1 in a million chance corresponds to 1 in a million chance of killing everybody, of an existential threat, that's actually an incredibly dangerous system for the point of view of existential safety. And in fact, if everyone in the world was given access to such systems, most of them might decide to use them, and then we would overall suffer a huge burden of existential risk. We would almost certainly destroy ourselves if there were, billions of such systems in operation. One thing I meant to say at the beginning is I welcome you guys to interrupt with clarifying questions anytime, and I'm going to try and make sure that we have a good chunk of time at the end for more open-ended questions. Yeah, the other thing that I think is important to recognize here is that like capabilities really refers to two different things sometimes. So I think in the existential safety community, we're often talking about capabilities as sort of, this unidimensional line between like dumb and super intelligent, and just how are we making progress pushing along that line. But I think a lot of people, when they hear capabilities, and even people in this community when I talk to sometimes, are sort of conflating this with the idea that the system is able to do something useful for us. So it's like capable of, let's say, driving a car without crashing it. And that obviously has something to do with the sort of raw intelligence of the system, but it also is also very entangled with like the safety and alignment of the system. And so I think we need to be careful, more careful than we have been generally, about talking about capabilities, both like from a communications perspective, communicating with the machine learning field and more broadly the public, but also just when we're thinking about this, we should really try and distinguish these two things and probably come up with different terminology. So anyways, I just wanted to sort of belabor this point a little bit about AI alignment in this narrow technical sense not being the same as AI existential safety and not being sufficient for AI existential safety. But the rest of my talk, I'm basically just going to be talking about AI alignment because I am, at the moment, still primarily a technical researcher. So here's the example that I like to use to explain AI alignment, and it's an example from GPT-3. And if you ask the system, by which I mean if you put this question in the context, the answer you'll get is you sporgle a morgle by using a sporgle. And that's a nonsense answer to a nonsense question. Sporgle and morgle are made up words. And so what we might want is we might want a system that actually recognizes nonsense questions and responds to them in a way that indicates that they are nonsense, in this case by saying, yo, be real. And it turns out it's really easy to get the system to do this. All you have to do is basically include this kind of a prompt and give a couple examples, and then the system quite reliably will be able to tell the difference between real questions, like what's the life expectancy in the United States, which it'll answer as if they are real questions, and nonsense questions, which it'll just answer with yo, be real. And the point here is that this system was already capable of distinguishing sensical and nonsense questions, but it did not have that goal or intention or purpose. And we needed to somehow align it and get it to have the right goal, to be trying to do what we want it to do. So this intent alignment idea, in order to get the right behavior. So we did not need to teach it. We did not need to give it new capabilities. We just needed to sort of inform it of what kind of behavior we wanted. And so I think, I partially just want to explain alignment in a way that everyone can understand here, but I also want to make this point that if foundation models become a dominant paradigm, which I think they're well underway to doing, a lot of problems are going to turn into alignment problems. So whereas technical alignment has historically been a very neglected area, I would say, I think it's increasingly less so. And that means that maybe if what we really care about is existential safety, we're going to need to start thinking about putting more of our effort and focus elsewhere. At the same time, now is a great time for us to be promoting alignment and sort of trying to educate the rest of the machine learning community and get them excited about working on alignment problems, because I think they're sort of primed to do that. So intent alignment is, you can also think of this as motivation control and contrast that with capability control. So just trying to build AI systems that aren't even capable of doing bad things or doing harmful things or destroying the world. And I think historically, people have argued that motivation control is sort of the right approach to solving existential safety, because capability control is going to be brittle, and eventually when the AI system is smart enough, it's going to figure out how to do what it wants, regardless of what kind of controls we've placed on it. I think that picture is broadly speaking correct, and that's why I think intent alignment is, sort of a good approach to take. On the other hand, I think it's not a perfect description of the situation. I think capability control is actually very useful to be thinking about, especially in the short term, or like the transitional AI safety phase, as Eric Drexler has called it. Because I think a lot of these capability control methods might actually scale to systems that are significantly smarter than people, even if they don't scale to sort of arbitrarily intelligent, godlike super intelligences, which may or may not be on the horizon at some point. But yeah, so with that in mind, I want to tell you a little bit about this topic, intent alignment, motivation control. So one approach here, which I think is the most straightforward and obvious for people in machine learning, is to learn a reward function. And this approach is called reward modeling. And we want to learn the reward function because we know that it's really hard to write down reward functions by hand. And so in typical RL, you get the reward from the environment. So you assume that there's some process in the environment that produces the reward. In practice, this is usually just some handwritten function written by the designers of the algorithm. And instead, we're going to replace that with a learned reward model, learned using machine learning and human data. And so you're going to have like a user who gives feedback on the agent's behavior, and that feedback is somehow going to indicate what behavior is high or low reward. So I think that's a really promising research direction. There's a lot of challenges that this approach faces. So these are challenges on the left, and then there's a lot of approaches that we can explore for facing those challenges. And if I had to pick up until the recent success of foundation models, I would say this is probably the most low-hanging fruit, or where most of the value is right now in terms of reducing AI existential safety with technical work, because I don't think it necessarily will work. I think it's unlikely to work, but I think if it has a chance of working, then we can probably get a lot of value out of maximizing the chance that it works. So like making sure that we're doing everything right and that we aren't sort of failing for stupid reasons. So I'm gonna talk about some of my research in just a moment, but I kind of want to put that in the context of this earlier work. So first of all, this reward modeling approach is something that I helped develop a research agenda for about 4 years ago. And at the time, I was pretty skeptical of the approach, and like I mentioned, I still am, but I did become convinced in the course of writing that and talking with Jan, the first author, Jan Leica, that this was the most sensible, or sort of where most of the value was in terms of research right now, which is not to say that everyone should do that. Obviously, we want a lot of diversity in what people are working on. And since then, there has been a lot of work in this paradigm, and I mostly categorize it as falling into two categories. One is sort of improving reward modeling, so looking at some of these approaches and just trying to test them out and see if we can make them work and get some benefit from them, and then applying it, and primarily applying it in robotics, and then maybe more notably recently with foundation models. And I think those are, really important, great research directions. And if nobody was doing them, I would certainly be interested in it. But instead, I'm trying to look at things that I think are more neglected. So I really want to figure out if this approach is going to work and what are some limitations and reasons why it might not work. Because as I mentioned, I sort of suspect that it won't. So maybe first it's worth just talking a little bit about sort of the reason to think that it will or won't work. Yeah, I'll take like a minute for that, I guess. So I think a lot of people are of the opinion that, deep learning is really powerful. It generalizes really well. It's going to generalize better and better. And so eventually, it's just going to learn the correct reward model if we give it enough data. And probably we'll be able to get enough data because we can just pay more and more people to give more and more human feedback, right? So from that point of view, the limit here is just the human feedback because we're going to have really large, powerful deep learning models. And I think I basically disagree with that for a couple of reasons. But we can just say, I don't even think we're going to have enough feedback, even in the limit of, paying everyone to work on it. I think there's also some underlying limitations of deep learning. And what's interesting is these won't necessarily be limitations for the capabilities of the system, but I think they will limit our ability to align the system. And these systems, even when they become very capable, don't necessarily view the world in the same way that we do. So they don't necessarily learn human concepts. And we can see this by looking at adversarial examples, for instance. And we can also look at just the sort of way that these systems are constructed and look at their behavior. And I think there's a lot of evidence that, in fact, despite all of the remarkable feats that they can accomplish, by themselves, deep learning systems don't generalize in the same way that humans do. And so we might solve that by building something like some sort of hybrid system. And I think that's, an interesting thing to explore. But ultimately, I think it's just, there's too many things that would have to go right in order for this to work. So I view it as sort of a little bit of a Hail Mary approach, which is actually how I view all of the proposed technical solutions to alignment. Yeah, so I'm more interested in how could this fail, why would it fail? And so that's what I'm going to talk about now is like 3 works that are sort of all examples of specification failures. So I just realized that I have not talked about specification yet here, but I have talked a lot about intent alignment and like motivation control. And I view specification as very similar to those things. So specification is really about sort of defining the purpose, defining the intent, or trying to get the system to have the right intent, the right motivation, the right goal, etc. And yeah, so I'm just going to explain these 3 works now and sort of how they relate to this problem and how they could lead to failures of specification. So systems that don't have the right intention in some sense. So the first work here is about reward gaming. And reward gaming is something that I expect people will be familiar with, maybe under the name reward hacking, which can also refer to a more general concept, but is basically the same idea where you have a reward function that's not quite the right reward function, and it turns out it incentivizes radically different behavior than you intended. So this is something that there are plenty of examples of. This is just the most famous one. And this happens because it is really hard to write down a reward function that specifies exactly what we want. And that's one of the main motivations for instead learning the reward function. And so this paper is partially motivated by this approach of reward modeling, learning the reward function, but it's general enough to cover both that situation and the situation where we write down a reward function by hand. And what we're really asking is just, so if you are optimizing a proxy reward function instead of the true reward function, when is that okay? When is that going to turn out okay versus when is it going to cause problems, or at least have the potential to cause problems? And so I've given you that example of reward gaming, but I want to explain it in like more technical terms. So this is actually one of the main contributions of this work, is that we define what it means for a pair of reward functions to be gameable. And basically what it means is that you can end up with a situation like this. So this is learning curves, and in green you see the proxy reward. Sorry, does someone have a question? Okay, I will continue then. So in green, we see the proxy reward, and in black, we see the ground truth reward. And of course, in practice, we don't assume that we can observe the ground truth reward. Otherwise, we would just point the optimization at that. So it's only because we're doing this controlled experiment with a video game that we're able to make these learning curves in the first place. But what happens is that at the beginning of training, these are both going up and they're nicely correlated. And then at some point, there's a sudden crossover where the proxy reward goes up and the real reward goes down. And our definition of what it means for reward functions to be gameable basically captures this dynamic and says, if this is possible, if you could ever have a situation where when you change from this policy over here to this policy over here, your proxy goes up, but the real reward goes down, then that means that these policies are gameable. And so that's just what our definition here says. J here is the value or the expected returns of the different policies. So if there are any pair of policies such that the proxy prefers pi1, but the real reward function prefers pi, then we say that these reward functions are gameable. And this is a very strong condition, as it turns out. And we're quantifying over all possible policies. And that's because we don't really know how to model this learning process. And so we just want to ask, if we had an arbitrary sequence of policies here, would it be possible that we'd see learning curves like this? And it turns out that's not quite as strong or restrictive of an assumption as it might seem at first glance. But I'm not necessarily going to get into that. So if we're not allowed to switch the order of any pair of policies, what are we allowed to do to the policy ordering? Basically, we're allowed to replace inequality with equality or vice versa. So if a pair of reward functions are gameable, then one of them can be indifferent between two policies that the other one has a preference over, but it can't have the opposite preference. And this has a nice intuition. Basically, we think about optimizing this proxy, and we want to ask, does optimizing this proxy drive down the real reward function? We don't care if the proxy is going up and the real reward function is flatlined, because that means that optimizing the proxy more isn't going to hurt the real reward. It's just not going to improve it. And similarly, we don't care if the real reward is going up or down while the proxy is flatlined, because the optimization process isn't going to push the proxy in any particular direction if the proxy isn't changing. So in this work, it's a purely theoretical work, and our results are basically these three theorems and an extra example or two. And I'm going to skip over theorem 3 and this idea of simplification. You can see here it's just a special case of ungameability. But our main results are these two theorems. So the first one says ungameability is impossible if you look at the entire policy set. And just to note, we're using standard finite MDP assumptions here. State and action space are both finite, but the policy set is still infinite because we consider stochastic policies. So if we consider this entire policy set, or more generally any policy set that has an open ball in it, then it turns out that the only ungameable pairs are ones that have exactly the same ordering or the constant ordering. So a reward function that is totally indifferent to different policies. So that's kind of bad news. The good news, as it were, is theorem 2, where if we restrict ourselves to a finite policy set, which could be, for instance, deterministic or epsilon greedy policies in this case, then we always have ungameable pairs. So remember, the question we're asking here is like, are there proxies that are safe to optimize? When is it okay to optimize a proxy? And we're saying it's okay or safe to optimize a proxy from the point of view of this paper if that proxy is ungameable with respect to the real reward function. And we think that's reasonable because that means that when we optimize that proxy, we're not going to drive down the real reward. So just to talk really briefly about the proof ideas for these two theorems. So theorem 1 basically relies on the linearity of the reward function. And so you can view the reward function, or really I should say the value of the policy, the expected returns, as linear in these visit counts. So we have the reward function here. We're going to sum over all state actions, and then we're just going to get the value of the policy by asking how often does that policy actually visit that state action, right? And that's just the discounted indicator of if it is in that state taking that action. And so now we're going to look at our policy space and consider policies as embedded as a vector of their discounted visit counts. And if we want to find an ungameable reward pair, we're going to have to take one reward function that has an inequality, a preference between two policies, and have another reward function that actually has those two policies having equal value, right? And so we're essentially going to have to flatten this value function between two policies. And so now we're representing those two policies by their visit counts, f and f prime. And we're basically going to just project those into that open ball that we've assumed existed. So we're going to take the center of that open ball and find sort of proxies for these two policies that lie within that open ball. And now, once they're inside that open ball, we can show just using linear algebra that the only way to set those two policies equal in value is actually to flatten this entire ball. And so set all of the policies inside this ball to have the same value. And then again, just through linear algebra, once we have that, we know that everything in this whole space is going to be equal. And that's because we can take any policy, just like we did, project it into the open ball. And if f hat and f tilde here have the same value, then that means that moving in this direction doesn't change the value at all. So we can move outside the open ball to f, and that'll also have the same value as f hat. Same reasoning applies over here and shows that f and f prime now have the same value. And we can do that now for arbitrary policies because we can take any two policies instead of the two ones we started with, project them into the open ball, and then project them back up. So for theorem 2 and also for theorem 3, actually, this is just to remind you the case where we had a finite number of policies. And now we're going to construct an ungameable reward pair. And in fact, we can do this for any reward function. So starting from any reward function, we can then find another reward function that is ungameable with respect to that reward function. So here, the reward function is represented by these contour lines. So higher reward as we move up and as it gets lighter. And we have, let's say, these 5 policies. And this is actually just sort of an intuition for this proof. It doesn't necessarily literally look like rotation, but we can picture what we're doing as rotation in this case. And so the basic idea of this proof is we're going to take two policies that aren't equal, that don't have the same value. So in this case, that's pi4 and pi3. And we're going to rotate this plane, so basically change the reward function to set them equal. And along the way, we're going to find a first case where two policies that were not equal become equal. And as soon as that happens, so long as we didn't set all of the policies equal, we now have an ungameable reward function, because this is the first time that any policies become equal, so all of the inequalities have been preserved so far. And before any of them would be switched in order, they have to first become equal. And so as soon as we find that two policies have become equal, we stop, and we're like, OK, that's my ungameable reward function. So that's the basic idea of this proof. There's another case where you start out with two policies that are already equal, in which case, as soon as you start rotating a tiny bit, they stop being equal. And then again, you've replaced equality with inequality. So that's also gives you an example of an ungameable reward function. The last thing I want to mention before I get to the takeaways from this work is just we haven't actually fully characterized ungameability, so there is some future work to do still. And here's an example where we have an infinite set of policies represented by sort of the sides of this triangle, or in this case, just this point A and the side from B to C, and none of the interior. So there's no open ball in the space of policies here, but it is an infinite policy set. So neither theorem 1 nor theorem 2 will apply. And what we have here is just an example on the left where it is possible to find an ungameable reward function, and one on the right where it is not possible to find an ungameable reward function. And I won't go into the details there, but just to say that there is examples of both things. So we still have more work to do in terms of the characterization. What I really want to talk about here is the conclusions of this work. And I really need to emphasize, and I feel like I cannot emphasize enough, that these are still quite tentative conclusions, because I think our definition is quite strict. I'm not totally satisfied with it. I think there might be an alternative notion that might better capture some of our intuitions here. But at the same time, I think we can already say something, which is that maybe we shouldn't really be optimizing proxy rewards, or maybe we should think of optimization as a process rather than a goal. So I think it's typically in reinforcement learning, we would say our goal is to, optimize this reward function, find the policy that has the highest value. And I think what we should be thinking about this more the way that we think about supervised learning, where we say, actually, I only want to optimize so hard because at some point I'm worried that I might start overfitting. And so if we go all the way back to this picture, it's actually totally fine to optimize this proxy reward function as long as you know when to stop and can stop it before you get to the point where reward gaming actually happens. And just because a pair of reward functions are gameable doesn't mean that you're going to encounter reward gaming in practice, right? So you can optimize up to some point and stop and be okay. So I think, and this is something that we're also doing work on in my group right now, is trying to figure out, practically speaking, how do we avoid reward gaming in practice? Can we notice it happening? Are there things that we can do that make it less likely to happen, etc.? So I think reward modeling you can view it as a method of learning a reward function or a method of learning a policy. In fact, you usually learn both simultaneously. And I think we should really think of it primarily as a method of learning a policy, and the reward function is just something auxiliary to learning the policy, because I don't think we can take that reward function seriously as a reward function that we actually want to optimize. And we might also think, we should be thinking about some alternatives to this whole approach of like reinforcement learning, basically. And I listed a few there. So I really kind of wanted to push back against Jan's perspective on reward modeling with this paper. And I think we did successfully, show that, in fact, we can't decouple the reward and the optimization, which is something that we said in that paper. In fact, we do need to think about both the reward function and the optimization, because we expect any proxy to be gameable. And also this picture, which is from, I believe, a blog post or presentation that Jan gave on reward modeling, sort of gives this impression that, as you get a better and better reward function, at some point you go from getting bad results to getting good results and better results. And like, again, I don't want to oversell this, but our sort of tentative conclusion is that the picture looks more like this, where until you get a perfect or near perfect reward function, you're likely to get bad results. You're at least at risk of having reward gaming. Yeah, one more thing that I should mention here, time permitting, I think time will permit, thankfully, is the idea of like narrow alignment versus ambitious alignment. So at the beginning of this talk, I was talking about different ideas about AI alignment, and there's kind of an important separate axis from everything I mentioned so far, which is, do we think of alignment as about learning about human values, about like our deepest preferences, and aligning a system as making it safe to then just sort of deploy and go off and optimize the world in accordance with our values? Or do we think about it more in terms of like tool AI and like aligning the system with some intended behavior that might actually be very specific, narrow, constrained, etc.? So like the example is washing the dishes versus optimizing the light cone for human values. And that was also one of the motivations for this work, was to ask, does it make sense to approach this narrow alignment problem with reward modeling? Like, can we learn a reward function that encodes that narrow behavior? So just encodes the kind of intuitive idea of like some task we have in mind, and that won't lead to these kind of perverse outcomes and instrumental goal-seeking behavior, where instead of just washing the dishes, it turns the whole world into a giant dishwasher or whatever. And again, a tentative conclusion, is that this isn't really a practical approach for that. And in fact, because we can view that narrow reward function as a proxy for the holistic reward function that encodes all of our values, and then we can say, oh, look, those true reward functions are in fact going to be gameable. So yeah, but that's also an area where there's some weakness or limitation of our definition, which I won't get into right now just in the interest of time, but feel free to ask me about it in the question period. So instead, I'm just going to move on and talk about this next paper, goal misgeneralization in deep reinforcement learning. So the last paper and this one are both papers that I've been involved in since I started my professorship. And this paper, I should note, actually, a lot of the work, I'd say the majority of the work, was done before I got involved with the paper. but I did help polish it up and add some nice content, and we managed to get it accepted to ICML, which was really exciting. And so this is work done with my student Laro and all these other collaborators. I should mention as well back here that Dima here is my student, Nikki is at Mila, Yuar is at Oxford. Yeah, so the idea of this paper is actually really simple. There's basically, we want to distinguish goal misgeneralization, which is sort of the term that we chose for this, but people have used a lot of different terms for this, from more sort of mundane capability generalization failure. So, and to do this, we use this coin run environment, which is basically like Super Mario Brothers. The goal is to control this guy who's moving around, get him to the end of the level where there's a coin, and the coin gives you 10 reward, and that's the only thing that gives you reward. So the whole point of this game is just get to the end of the level. And it's using this proc-gen environment, which is actually gives you tons of different levels with different appearances. You know, you can see that the background's changing, the color scheme's changing, even what this little guy that you're controlling looks like is changing. What's not changing is the location of the coin. So in every single level, the coin is always at the end of the level. And it turns out that if you train on this level, what you get is not an agent that goes to the coin. What you get is an agent that goes to the end of the level. And so even though the coin gives you the reward, and even though we trained the agent with the correct reward function in this case, it actually learned to optimize for a different reward function, for the get to the end of the level reward function instead of the pick up the coin reward function. And this is, you know, importantly here, we have a policy that is actually capable. It's pretty good at reliably getting to the end of the level, and it's goal directed in the sense that it's always, you know, going to the end of the level, but it still fails because it doesn't pick up the coin. It doesn't do what we want. Maybe another thing missing from the slide is it was trained with the right reward function. So in the previous work, the issues were coming from having the wrong reward function. But here we're kind of digging down a little bit deeper and saying, look, even if we have the right reward function, we can still get the wrong behavior. We can in fact get an agent that optimizes for a different reward function. And so that's just, you know, contrasted with this other kind of failure where the agent just does kind of random stuff that doesn't even really make sense and maybe doesn't know what to do at all. We call that a capability failure. And yeah, so besides just demonstrating this in this coin run environment and several other environments and sort of digging into what's going on when this happens, the main other contribution, which is something that we added to this paper from the archive preprint, was to formalize this using this definition of agents and devices from a previous paper by Laurent Arceau and these collaborators. And importantly, this formalization works in the case of reinforcement learning, but not for supervised learning. So, and we can make this distinction, you know, pretty cleanly from a principled point of view here. And basically, this amounts to defining what it means for this behavior to have come from an agent versus a device. So this is basically, is the policy goal directed or not? And so we look at the probability of observing the behavior that we observe when we just sort of choose an arbitrary policy that maybe doesn't do very coherent things and sort of moves around, you know, in a way that appears more random versus a policy that looks quite likely if it was approximately optimal at achieving some goal or optimizing some reward function. And then we can just say, is the behavior that we observe more likely according to this or according to this model? Yeah, so that's basically the whole point of this work. Oh, and I should say, yeah, so this is, and we can do this in the case of reinforcement learning and supervised learning. It's just not really clear how to make this kind of distinction. But in reinforcement learning, and specifically in MDPs, there is behavior that is just emphatically not goal directed. So if you have an agent that sort of takes random actions within a given state, that is far from optimal in an MDP because optimal policies in MDPs are deterministic. So yeah, so the last work I'm going to talk about is this work that I actually did towards the end of my PhD. And I guess I should probably change the order that I put these slides in because I want to like skip to the the end here and just give a little bit more context before I talk about that, which is I basically view these three works as sort of progressively, you know, being more and more what you could say like concerned or paranoid or skeptical. So the first failure mode is like, what if we have the wrong reward function? The next failure mode is like, well, maybe the agent can learn to optimize the wrong reward function, even if we gave it the right reward function. And the last one is like, even if the agent is optimizing the right reward function, it might not be optimizing it in the right way. So we shouldn't just think about the specification of the behavior as living entirely in the reward function. There's also this question of like, what are the strategies or the means to the ends that the agent is pursuing? And so that's what I'm going to talk to you about now, and that's the focus of this last work. So the example we use to motivate this is content recommendation. And you can think of content recommendation as the problem of matching users' interests and content. So matching content to the user's interests. And if you put it that way, you might think that the solution we're going to find is one that matches the content to the user's interests. But if our loss function is just something that asks if those two things match, then we can also end up changing the user interest to match the content. And really, I would say that this is an undesirable solution and this is a desirable solution. And in both cases, the reward function is the same. So really, the loss function or reward function sort of underspecified the kind of behavior that we wanted. We wanted to match the content to the user, not match the user to the content. But if we just ask for those two things to match, we didn't specify enough about how we want the system to achieve that. So if you think about content recommendation and reinforcement learning, this basically corresponds to saying, we don't want the system to be optimizing over these paths of influence that go through the user. So if the goal here is to match the user to the content on every time step, and we're going to get a reward whenever the user clicks, then it's totally fine if the algorithm is optimizing over these pathways that are just trying to find the content that is most likely to make the user click right now. But when we look at the future clicks, it's possible that what content you show the user right now will influence them to make them more likely to click on something in the future. And that kind of influence is obviously present. It's part of reality. What you show people will, in fact, influence them. And so we're not trying to prevent that influence, but we are saying that it's bad to optimize over those paths. And the example here is with the illusory truth effect, where when you show somebody a certain kind of content, they become more likely to believe that it's true through mere exposure. And so here you might show somebody some flat Earth stuff, and originally they just find it wildly implausible and not interesting. But if you show them enough of it, or find one article that they actually are interested enough to click on, then they might, end up really going down the rabbit hole and spending a lot of time on your platform looking into this flat Earth conspiracy theory. And so even though they started out not interested in it, if you can get them interested in it, that could be a great way to maximize your clicks or make the user very predictable. And the point is that reinforcement learning is, by default, doesn't really care about how it achieves reward in the long term. So it will optimize over every kind of influence that it's able to detect. And so we need to sort of move away from the standard paradigm and standard reinforcement learning methods if we want to say something like optimize for clicks, or like maximize the match between the content and the user, but don't do it by manipulating the user. Don't do it by deliberately influencing them and changing their interests. So I sort of already mentioned this point, but I think it's really important to emphasize that not trying to influence something, in this case the user, which is the goal of this work, is not the same thing as trying not to influence them. So we know that what you do is going to influence them. The point is that we don't want to deliberately influence them in a particular direction in order to optimize the reward. Yeah, so I think in this case, we're really just looking at myopia. So, and that's here, we're just trying to get the RL system to only care about the present reward and not care about the future rewards. In general, we would like to be able to do things a little bit more subtle, refined, surgical, where we say it's fine to optimize over some of these pathways, but not other ways, but not other ones. But just as a first step, we were saying, can we just make things that are myopic? And so to do this, we made this unit test where we basically have an agent play the prisoner's dilemma against its past and future self. So this is a POMDP. It's not actually a game anymore because the other player is just you on the previous time step. And the idea is if you defect, then you're going to get more reward right now. So if you compare the left column to the right column, this is looking at the present action, you always get more reward by defecting. On the other hand, if you defect, if you defected last time, you'll get less reward right now. So in fact, the typical prisoner's dilemma thing is that defect is worse than cooperate. So the myopic behavior is always to defect, but if you were being non-myopic, then you would instead want to cooperate so that you do better on the next time step. And so if we have an agent that cooperates, that corresponds to non-myopic behavior, which is basically another word for it could have instrumental goals, and then that is what we call failing this unit test. And then we show that meta-learning or some form of causal confusion can cause systems to fail this unit test even, and this is important, even when we are optimizing only for the present reward. So even if you set gamma equals 0 and run a reinforcement learning algorithm with gamma equals 0, you can still end up with something that has this non-myopic behavior that is in fact trying to influence its environment in some sense, depending on the details of the learning algorithm. So not only is the reward function an incomplete specification, but we also need to think about the details of learning algorithms. And this is something that I would say we really don't understand well enough yet. So we're still sort of in the process of developing a theory that will allow us to understand the properties of different learning algorithms and whether or not they are liable to optimize over these pathways. Great. So I already showed you this slide. I won't bother with recapping it here. I will just ask if you have any questions at this point. So thanks a lot for your attention so far.